Welcome folks, and in today's lesson we're going to talk about why molecules behave the way that they behave. What causes molecules to have certain properties, certain characteristics, and it comes down to both the polarity of said molecule, and which is dependent on the bonding and the shape. So just a quick review here. When we talk about compounds, we need to understand that it's a combination of two or more elements, and we need to also go back and talk about why this happens, and it is tied into the yearning for a full outer shell, which is sometimes called the octet rule, and it's just in terms of energy it's a more attractive proposition. So the sodium gives away an electron to fluorine, we get ions form, and we get more stability as a result of this ionic bond. We should also talk about electronegativity. Some elements have a stronger attraction to electrons than others, and if you want to think about it in terms of a flower, some flowers have a stronger attraction to bees than others, and so too certain elements such as fluorine, for example, have a much stronger attraction to electrons and will want to take on electrons much more than elements on the left of the periodic table, for example. So what does this mean in terms of bonding, and what does polar covalent bonding mean? Well, all atoms do not attract electrons to the same amount, and so this is important when we're talking about bonding which is not ionic bonding, when there's a sharing of electrons. And so you can see the one on the left, the picture on the left is fluorine bonded to fluorine, and of course both of those have the same electronegativity values, so they will share that electron equally. However, if we look at hydrogen bonded to fluorine, the fluorine will want that electron close to it a little bit more. So the electron's going to spend more time in this teal area, and because of that it develops this partial charge, which is just a delta. It looks like a small d. That's used to represent sort of like a mini charge, not a full ion yet, but getting there. So one can determine the degree to which electrons are transferred or shared by looking at electronegativity values. And so if we look at this on screen, we can use a bonding continuum, and we can look at the difference in electronegativity values and see if they are between 0 and 0.5. If they are, then it's a non-polar bond. That means the electrons are shared equally, because the electronegativity difference is small on those elements. If it's between 0.5 and 1.7, it's a polar covalent, and if it's greater than 1.7, it's an ionic bond. If we look at CH4 or methane, we have a look at its electronegativity values for carbon and hydrogen, and we will see that if we take those away, we see what it is for carbon, which is 2.55, and hydrogen, which is 2.20, and then we just take those values away. We're always going to get a positive. We cannot get a negative. We'll see that it's 0.35, and that makes it non-polar. In other words, the electrons are shared somewhat equally. If we look at NH3, which is ammonia, it's a different scenario. We get their electronegativity values, and we see that it's a polar covalent bond. So still shared, but shared unequally. And if we look at lithium oxide, we can see that the oxygen is going to want those electrons a lot more. So this is what we commonly refer to as an ionic bond. We should also talk about dipole moments. Dipole moments exist where you have that unequal sharing of electrons, and you have that partial positive, partial negative, and we get this thing called dipole moments. And the dipole moment is represented by the red arrow, and it always points towards the partial negative, the one that's taking the electrons for a little bit more at a time. If we look at water, it's a good example of a polar covalent bond, where the oxygen is going to hog those electrons a little bit more, and so we're going to get a dipole in our arrows heading away from hydrogen towards oxygen. So if we look at hydrogen bonds, or if we look at the molecules of water, we can see that there's a very strong bonding between them. And the reason is because these dipole moments here, these positive dipole moments, will go out and will seek and attract and bond to these big negative dipole moments from other water molecules. So the water molecules have a very tight bonding between their molecules. And that's because one side of the molecule is presenting a positive and the other side is presenting a negative. So it's asymmetrical in terms of its dipole moment. So the shape of polar molecules, in addition to bonds being polar or non-polar, a molecule's polarity can be based on their shape. So when you're talking about the shape of a molecule, you've got to ask yourself whether it's symmetrical or non-symmetrical. And if we want to look at the polarity of a molecule, we have to look at the bonding within a molecule, and we have to look at its shape. So here's an example on the left. We've got a water molecule. You'll see the Lewis representation of the electrons on the central atom here. These electrons are actually really important. And the reason is because the electrons will, because of they're the same charge, they will actually repel and push away those other electrons. And so they'll push these bonds, they'll push this oxygen-hydrogen bond downwards, and they'll cause the shape to be asymmetrical. And if we look at the one on the right, this is a non-polar molecule, methane. All the hydrogens in methane are pulling the same strength. And what's more, even if the bonding is polar between the carbon and hydrogen, the molecule of methane will only be presenting this dipole on the outside, which is only a positive dipole. In other words, the negative side of it is hidden. And so not all molecules with polar bonds are polar molecules. A good example here would be boron trifluoride, where we have a polar bond between the boron and the fluorine. However, because of the shape and because there's just a negative dipole presented on each of these sides, and the fact that it's very symmetrical, there won't be that polarity of molecules. So polarity of bond, but the molecule itself is nonpolar. Another example would be the carbon bonded to 4 chlorines. And this is a very common shape in chemistry. It's called tetrahedral. And again, you can see that this dipole on the outside presented will just be one type of dipole. It'll be a negative, and the positive is hidden, if you like. So if we look at a GIF of this is methane here, and just to show you in 3D that the positive dipole is right in the center. It's hidden, and therefore it won't be as easy in terms of reaching out and finding negatives. And it presents just that negative dipole on the outside caused by the chlorine or the hydrogen, or in this case I guess it would be positive because hydrogens are positive relative to the carbons. So if we look at it in terms of dipoles, again we should now understand the way the arrows are running. Again, it's important to say that it's symmetrical, and this means that it's non-polar as a molecule. And this GIF hopefully shows you the problem in terms of polarity. We have the partial positive charges going and looking and seeking to attract that negative, but the negative dipole is hidden, if you like, in the center. So different shapes of molecules. So we said that it was dependent on two things: the bonding between the atoms in the molecule has to be polar, and also the shape has to be asymmetrical. But what about the different shapes of molecules? Are they all the same shapes? Are they all asymmetrical or symmetrical and just, one or two shapes? And how would we find that out? So the first thing we should do is we should draw a Lewis dot diagram and follow good rules when doing that. We would look at the atom or element that's likely to have the most bonding capacity. In this case, for NH3, it would be nitrogen. And then we would share electrons like here, so that all of the atoms can have a full outer shell. Again, that isoelectronic property. They want to have stability. And we'll see that there's 2 electrons left over here. They are non-bonded. They are what are called a lone pair of electrons. Now, similar to before, they're actually going to push down on these 2 bonds on either side, and they're going to cause that asymmetrical nature. So the asymmetrical nature is very often caused by lone pairs of electrons on the central atom. So we determine the central atom, we look at how many electrons each atom needs to gain in order to have a full outer shell, and we determine if multiple bonds are needed. In this case, we didn't need double or triple bonds to do that, just single bonds. And we determine the structural shape based on 2 things. The number of atoms bonded to the central atom. For NH3 it was 3. And the number of lone pairs of electrons. And there was 1 lone pair, if you remember, for that. So these are the 3 bonded pairs. 1, 2, 3. And this is the lone pair here. So 3 bonded pairs, 1 lone pair. And we would then consult a table of values or of shapes that was developed by Dr. Ron Gillespie way back when, and he sought to put some theory and structure behind the shapes of molecules based on electron repulsion. And so we can see, if we look at our ammonia from earlier, there was 3 bonding pairs, there was 1 lone pair, and that would give it the shape of triagonal pyramidal. It's important to say that there is different shapes here, common shapes. So for example, water is a bent shape because it has 2 bonded pairs, and it actually has those 2 lone pairs sitting on oxygen. And so it has a bent shape, and these different shapes have different angles between the bonding pairs. So just to go back and review which molecules are polar, you might want to stop the video here and just ask yourself if you can figure out which ones are polar. So the first one we're going to look at is nitrogen bonded to 3 iodines. We can see that there is a lone pair of electrons here. That's going to make it, and 3 bonded pairs. So we're looking at a triagonal pyramidal structure. However, is the actual bond, the molecule itself, polar? Well, the bonds between the nitrogen and the iodine are non-polar bonds, so that would suggest we've got a problem, even if the shape is asymmetrical, which it is. So the shape is asymmetrical, but no polar bonds, so it's a non-polar overall. What about silicon tetrachloride? Okay, so silicon bonded to 4 chlorines. Here we can see that the shape looks good, it looks promising, it is symmetrical. When it looks promising, that is to say, for non-polar. But even though there's polar bonds between silicon and chlorine, so we do have polarity there, we're not going to have polarity because of the fact that it's a symmetrical shape. So it's symmetrical and therefore a non-polar molecule. The final one is a carbon bonded to hydrogen and 3 chlorines. If we have a look at this one, we can see that particularly the carbon-chlorine bonds are polar. So that's the first step met. And if we look at it, we can see also that it is going to have those dipoles all on one side, right? So now we see a presentation of negative dipoles on one side and positive on the other. And because of that, it has a polarity asymmetrical dipole, and so it is a polar molecule. And we can look here, if we look at methane, there are different ways to show that. Overall, it has a common shape for 4 bonded pairs and no lone pairs, called tetrahedral. Because of that, it's non-polar. If we look at carbon dioxide, it is a linear shape and it is non-polar. And water, we talked about, has a different shape as well. It is a bent shape, and again, that's dependent on the bonded pair and lone pair, and it is polar. So hopefully you found this video useful in terms of discussing and trying to understand how the bonding and the shape of a molecule drives its polarity, which in turn is going to be very important in terms of driving how it behaves and acts and what its properties are.